So now going to define a very common, very widespread, important class of games, which is called congestion games. And as the name suggests, there are here several parties, several players in our language, which use common and finite resource, or several finite resources. And at each resource, the more players use that resource, the harder it is for them. So, for example, when they drive on the same piece of road, that piece of road is the common resource, then the more players use it, the less quickly the driving becomes. Of course, it depends on the piece of road. Some roads are very wide, so only when you have many players, many cars at that piece of road, will they feel that it's overloaded. Some roads are very narrow. If you have only one car who can go there and very slowly, perhaps, then of course it will be felt differently. So a general definition of a congestion game is as follows. A congestion game is defined by N, M, SIs, and CJs. Now, the definition is actually a bit long, but it's clear. So players N from 1 to N. The facilities, let's say pieces of road in the example I just mentioned, M, capital M from 1 to M. Now a player has strategies. SI are all the strategies of player I, and that is some subset of the subsets of the facilities besides the empty subset. So a player can choose which subset of the facilities from that player's SI the player is going to use. For example, if we give the example of a network of roads, then in order to get from my point of origin to my point of destination, I need to use a certain subset of roads in order to get there. But it can be several options, but each subset is a possible strategy. Then cost functions. They exactly quantify how hard it becomes when several players use the same piece of road. So for each J in M, for each common facility, Sj is a function from the number of users to the real numbers. And here it's a game of minimizing costs. Despite that, we will write utilities simply because there are cost functions. And now we are going to define, based on the cost functions, we are going to define the utilities of the players. But it's still the minimization of cost. So let's say a Nash equilibrium in this case, it's not where no player can increase her utility by unilateral deviations, but it's where no player can decrease her cost. Okay, how do we define the cost of a player based on the cost functions? So first of all, for each facility and strategy profile, we define the load of that facility given the strategy profile, and that's the number of players whose strategies include that facility. So those who use it. And the utility, therefore, of player I is the total cost over all the facilities the player uses. I look at the load of the facility given the strategy profile, and I look at the cost of that facility given the load, and the total cost of all the facilities the player uses is her utility. So we have now defined the players, and given the facilities, we also define the strategies as I is some subset of the set of all non-empty subsets. And given the cost functions, we defined load and utilities. So that is the definition of congestion games. And now let us give a classical, simple example. So the games in general, I can model traffic, computer networks, using common classroom, so that you have some finite resource which at least becomes less efficient when you use it, when too many people use it, too many players use it in general. So the example includes a network of 4 nodes and one v1, v2, v3, v4. And the cost functions of each of the edges connecting the nodes is c12, c23, c34, and c41. Now, excuse me. Now the network, excuse me, the set of players n includes 2 players A and B. It includes the possible facilities 1, 2, 2, 3, 4, 1, and 3, 4. So the possible edges, simply between 1 and 2, between 2 and 3, between 4 and 1, between 3 and 4. All those 4 edges. We assume there are no edges between 1 and 3 and 2 and 4 directly. And the strategies are as follows. The strategies of player A are those who allow that player to come from v1 to v3, which is either 1, 2, and 2, 3, so going like that, or to 1 and 3, 4, going like 4, 1, and 3, 4, going like that. The strategies of player B are all the routes that allow that player to come from v2 to v4. Formally, it's either 1, 2, and 4, 1, like that, or 2, 3, and 3, 4, 2, 3, and 3, 4. Here it's undirected. And I'm now asking you, as an exercise, to do the following. First, write this game as a normal form game. Then, a hint, it's a potential game. But prove it by writing the potential function. And the question is now, which congestion games in general have a potential? So this is an example of a congestion games which has a potential. Maybe we can characterize all the congestion games which have a potential. Okay, so the answer is, remarkably, there is a theorem, actually 2 theorems. The general theorem is that congestion games are isomorphic to finite potential games. So all congestion games have a potential. And moreover, all finite potential games are isomorphic, which I'm now going to define what it means, to congestion games. So first of all, let us. So one direction was proven by Rosenthal in '73, the person I think who introduced this notion of potential games. At least he was either the first or the first one to introduce this notion. And the second direction, that every finite potential a game is isomorphic, can be expressed as a congestion game, is a bit longer. Is a theorem by Monderer and Shapley from '96. So first, Rosenthal. Given a congestion game, the function p, which goes over all the utilities used in the profile, and for each utility it goes over from load 1 to the actual load in the profile, and sums up the c, so it does not simply look at the cost of the load. It goes from 1 to the load and sums up. That's a potential function for the game. Okay, that's in particular, of course, a statement that the game is a potential game, and the proof can either be shown from the corollary, where we just characterize the game as a potential game based on this general path of length 4, where 2 players change on the way, or we also can prove this directly from the definition of the potential, and the proof is as follows. So the proof is as follows. When player I changes her strategy. She starts using new facilities. I'm speaking, of course, in abstract terms now. It's not about traffic necessarily. It's not necessarily about traffic. It's a general potential game. New facilities M prime, and stops using some facilities M prime, M2 prime. Now the change to her utility function, player I is the only player to change, is the total cost of those facilities M prime in M prime, where the load has increased by 1, minus the total cost of the facilities in M prime 1, according to the original load. And that's exactly the change in the potential function. So that is a proof. Now, in order to prove the other direction, we first need to formally define what do we mean here by isomorphic games. So strategic form games on the same set of players N, G1. I should have written it differently, not as G1 and G prime, but as G1 and as G and G prime. G and G prime. G has N strategy space S and utilities UI. G prime has N, the same N, but different strategies. It's finite, but it actually does not have even to be finite. In this case, it does not have to be finite for the definition. S prime and the utilities U prime, UI prime, those are the utility functions. The games are isomorphic if for each player there is a bijection, so it's a mutual correspondence, which is 1-to-1 and onto. A bijection from SI to SI prime, from her strategies in the game G to her strategies in the game G prime, such that the utility of that player with strategy profile S1 till Sn, the utility of player, the correspondence we have, okay, the correspondence between the strategies of player I is Fi, and for each player we have such a correspondence. The total vector of those correspondences is the isomorphism, and the games are isomorphic if the UI, given the strategy profile, is the same as the utility of the, yes, I need to change it because I do have several typos here. My apologies. Okay. Now I've changed it, so the requirement is that the utility of the original profile is the same as the new utility of the profile, which is obtained from the original by those functions f1 and fn, which are applied on s1 till sn respectively. And the isomorphism is the set of the vector of functions. So we can rename the strategies such that the utilities will be the same for each of the possible profiles. So the game for any strategic analysis is the same. And the theorem by Mondel and Shapri is that every finite potential game is isomorphic to a congestion game. Okay, so in order to prove that, we are going to need some notation. We're going to give only the first part, or let's say the main part of the proof. There is some quite lengthy part we are going to omit, but we are going to give the main meat of the proof, the main idea. Actually, the proof, the formal proof. So simply, we are going to stop it at some point. So before the proof, there is the following notation. Given a strategy profile and players, some subset of players K, capital K, denote the profile of that subset of players K. So S applied on K as a function. Actually, we used to define that way the vector of the if k were a subscript, it would be simply the vector of the strategies of those players. But now it's like a function, so S gets k in the parentheses, and this is defined as the utility of the strategies, and strategies here are looked at as sets of the facilities, all the facilities which are used by all the players in this strategy profile. So in the example of a road, these are all the pieces of the roads which are used by those players in the strategy profile. And S of minus k is S of the others. So all the facilities that are used by the players which are not in K, who are not in K, in this strategy profile. And now also when K is a singleton, we can, instead of writing that it's S of the singleton, we can just write S of I. And analogically, instead of writing that it's S of minus the singleton, we can just write S of minus I. It's very similar to the normal notation. Usually simply when we define the strategies of certain players, we simply use that in subscripts, but here when we unite all the facilities used by the players, we use it as an argument to the function. Now the other notation is now not on the subset of players, but let's look at a vector of real numbers, a real number for each facility, because M is the set of facilities. Let us now look at a subset of facilities, B, and define the vector X applied on B as the sum, simply an arithmetic sum, of all the real numbers in Xi when I is in B. So all the real numbers which correspond to facilities in B. And now we can formulate a lemma, which gives another way to represent the utility in a congestion game. And that's a very nice, that's pretty much a reformulation, but it's a very nice reformulation. So given the congestion game, which has players N, facilities M, strategies S, and cost C, for any real any natural number. No, not oh, my apologies. It's not natural, of course. Natural would have two lines. For any player R, define X R as a vector in Rm, so a vector for each facility. As follows: the jth entity of that vector is defined as the cost of j's facility when R is the number of the users. So for each facility, we look what is the number of the users, and xr, the vector of the number of the users R, is the cost vector for each facility, such that the cost vector includes how much each facility costs. Then R is the number of the users of that facility. So then, for each player, for each strategy profile S, the utility of the player can be expressed as follows. Now we look at all the facilities. Aha. Here I've switched to the notation notification of the paper, and then it's going to be confusing, so I'm going to change that. So the lemma says that the utility of a certain player I at profile S can be seen as follows. So first, remember X I is, according to this definition, is the sum of the entries of vector which correspond to as x1 to a certain player. So